Hello, my name is Philip Adler, and I will be presenting the topic of Lab 4, which is the air pressure distribution over an airfoil and hot wire nanometry to measure the wake velocity distribution. The pressure distribution is going to be used to find the 2D lift coefficient of the airfoil and analyze the pressure drag at a high angle of attack. In the hot wire nanometry will be used to measure the momentum loss of the airflow flowing from the front of the airfoil to the back of the airfoil using a hot wire. And this will be used to calculate drag of the airfoil. Now, the outline of this presentation I'll start with the introduction and the background of the equipment and measurements, which is the hot wire nanometry and pressure test, and I'll go over how this works and how we'll be using it to generate data. The next part of that, my presentation will be the method of experiment, which starts with the hot wire calibration and the calculation of pressure distribution at different angles of attack, and the weight measurements, and how we're going to get the weight measurements, and then the next section will be results, is where I'll go over how we're going to calculate the lift and drag, how we're going to calculate the lift from the pressure distribution, how we're going to calculate the drag from the weight velocity distribution, and differences from the past labs, a little bit of the differences from the past labs, and I'm going to make conclusions about our results, and last will be the work side. So to start with, the hot wire nanometer, it operates by creating a voltage across the Wheatstone bridge, and it generates heat from the conduction through the resistor, and it loses heat through the convective properties of the flow. So the faster the flow is moving, the more heat's going to lose, and the higher voltage it is to stabilize the temperature. And the temperature will be stabilized by the feedback mechanism. The pros of hot wire nanometer, you might be asking, like, why don't you use a pitot static probe? Well, the reason is that pitot static probe, it averages across a larger area, and with the hot wire, you can measure this velocity gradings over a short span. Like, if you want to measure from point A to point B in a short span, there's a high gradient, you want to use this, and this over the pitot tube. Another reason is a good frequency response. We won't really be using that experiment because it's a study problem, but it's one reason why you might want to use this. The second equipment will be the pressure ports, and these are integrated into the airfoil. So we'll be looking at the pressure distribution at port at certain percentages of the cord, and we'll be using this to calculate the component in the lift direction, the drag direction at these pressure ports. Well, if you want to calculate drag, through this method, you'll be ignoring viscous effects, which are important for streamlined objects. Pressure distribution would be very important for a high angle of attack, airfoils, or a blunt object like a sphere or cylinder, but in this case, it won't really suffice for measurable drag distribution. These general methods, we start by calibrating the hot wire with adjusting King's law. So with a pitot static tube, we'll be calculating the known velocity of the wind tunnel, and then we'll be using the hot wire to measure the voltage. And then you plot these points, which I'll go over in the next slide, and calculate this. The next part is we're going to measure the pressure distribution over the lower surface and the upper surface. You can see it, there's going to be a 0, 7.5, 10, 20, 30, 40, 50, 60, 70% of the cord measurements on the upper and lower surface of the airfoil, but there will also be an additional measurement at 80% of the cord from the leading edge. All these are from the leading edge of the Clark White 14 airfoil at 0, 4, 80, 20 degrees at a free stream of 1025 meters per second. And then we'll be using the pitot measurement for inlet speed. For all our experiments, and then we'll be measuring the wake at angles of attack. So we use the pitot static measurement to know the inlet that pressure approaching the airfoil, and then you measure the weight, the velocity, so you know the pressure, the velocity of the airflow at the back end of the airfoil, so you can see the momentum exchange between the airfoil and the air. And this will account for both pressure drag and viscous drag. So our methods of analysis: one, you see here we calculated, this is the hot wire anometer, and this is the best fit line. Voltage curve with velocity 0.45. This is the adjusted King's law. We calculate here. We now know, given a certain voltage, given a certain voltage here is E, we know the velocity of the airfoil. The airflow, not airfoil. The second part, quantitatively, is calculations of lift from the pressure ports. So you can see here, the pressure will be acting downwards in the upward surface. So you see cosine data will always be negative. So always be positive on the upper and lower surfaces. The cosine data is the chord relative, it'll be the chord to the surface profile angle. And it can be calculated using this. If you make a triangle, and then same with the sine data. So yeah, this will be the component normal, and this will be the component axial, and then in the bottom surface is going to be flipped. The drag is always going to be operating the same. The drag is going to be operating the same way, given the same angle, but not the drag. I mean the axial force, but the normal force will be the same. And we'll use the dx, which will be like x from this next port to the current port. You could use that to calculate dx. So we're like splitting the airfoil into surface panels, and then measuring the pressure normal to that, pressure force, which will act net normal to that panel. And I'll be using that and breaking it into components in the axial normal direction. The next part is we have to adjust, we have to break the normal and axial components into lift and drag, because the normal is normal to the chord and not the normal to the free stream. The lift is normal to the free stream. So I need to adjust this angle of attack right here, the free stream relative to the chord, and this will break the lift and the drag into these components. And then we adjust the CL to C. We calculate the coefficient by L over. These will be the 2D coefficients, which in a theoretically high aspect ratio wing, which we're assuming will be the same as a 3D lift coefficient, and we'll be normalizing it, both the lift and the drag, by the dynamic pressure, which is 1/2 density times velocity squared times the chord. The next quantitative part of this experiment will be the drag, and we'll be looking essentially at the mass flow, which will be rho uy per unit span. This is all per unit span, and then multiplying it by how much velocity that is lost. We have to integrate this through it like a constant volume. So we're going to have to make sure that the same mass encompassed on the right side of this flow is the same mass on the left side, and we'll be pretty much calculating the momentum exchange. The airflow uses momentum in this picture in the leftward direction, and then the airflow uses momentum in the rightward direction, which will essentially slow it down in the airflow. So looking at our graph results, we can see that the velocity loss relative to the free stream is pretty, if you're looking at the left photo, is pretty small. So you can pretty much see that the pressure drag at high angles of attack is the main culprit in massive drag. There's still going to be drag at lower angle of attack, but you can see here how important separation is in calculating drag. You can see that there's a huge velocity loss at high angle of attack at 20 angle degree. And then you can see here using the wake measurements that this is a pretty large jump past the 8 to 25, and my guess would go really high past this point. Then looking at the lift coefficient, it's pretty close to what we did in experiment 3 when we used a sting balance to measure the lift coefficient. So they have their pros and cons. Pressure port can only measure discrete values, but the C mounts could have noise. Looking at, this is our CP. So you can see here, this is supposed to be positive and this is negative. So on the upper surface, like the CP will be negative, and the lower surface, CP shouldn't go above 1. The CP of 1 means all the dynamic pressure is converted to static pressure, and that should be the highest. And then you see on the upper surface, should be a lower pressure or negative pressure coefficient, which means the pressure is below the free stream. The conclusions is that pressure drag was completely obvious at an angle of attack over 20 degrees, and we can see this from the wake velocity. It did not sharply increase until between 8 and 20 degrees of angle of attack, and this is like our prediction of separation was about 15 degrees from past experiments where we use the tufts. And then there was nonsense values. Either my group made a mistake on the calculations or there was instrumental errors because the pressure coefficient shouldn't have been over 1. That's pretty much impossible for subsonic flow, at least. We're excited. Thank you for listening to my presentation. This is Philip, and thank you.